Welcome to spectroscopy. So we've just spent several weeks, months almost, looking into quantum mechanical systems and how do we represent one electron and how do we approximate multiple electrons. So now the question is, well, why do we care? Well, as chemists, we want to talk to molecules. We want to know what they're saying. Well, ask yourself, what are they saying? What have you learned about a molecule? Go team. So structural information, molecular geometry, bond lengths, ionization energies, that molecules even exist. All of that comes from spectroscopy, which means we are learning about energy states. But we're not learning about energy state 1 and energy state 2. We're learning about the difference between the two of them. Okay? So things I want you to take into account, or things I want you to consider as you dive into spectroscopy, is that we are looking essentially at an initial and a final state. Now, I don't want you to think about this as an electron in the ground state and going up to an excited state. It's not always an electron. It could be a vibrational mode. It could be a rotational mode. It can be nuclear resonance. It can be scattering. So it's not that you've got electrons always moving. It's that you've got, and besides, they're not really moving. They're waves. They're expanded out. You now know that they're no longer this picture. The electrons on the little orbits. That's wrong. Don't think that way. I want you to think about, there's an initial wave function, I'll write this way. There's an initial wave function psi that represents your entire system. There's a final wave function psi that represents your final system, whatever that system may be. A harmonic oscillator, a particle on a ring, which is going to turn into what's called a rigid rotor. It's a dumbbell that rotates, because rotations are also quantized. So you've got resonance, so nuclear resonance. So you've got wave functions that represent these different initial and final states. So transition occurs when the transition dipole moment is non-zero. So there's your transition dipole moment. It's the expectation value of that. And we can liken this to a probability of a transition occurring. The bigger that number, the more likely a transition happened. The lower that number, no transition at all. So when this doesn't equal 0, when this wave function, the transition dipole moment, operating on the initial wave function state here, when it is multiplied by this wave function state, basically what you're saying is that there's a wave function here and a wave function here, and there's some sort of overlap between the two. Go team, because think about what this means if it is 0. It means they're orthogonal to one another. No overlap whatsoever. But they're orthogonal when the transition dipole moment can't get them to overlap. Cool? So what we have is when they are non-zero, so when there is an overlap between the two wave functions, you've got a non-zero transition dipole moment, which means you would then know information about which wave functions satisfy this equation. And this is where we get our selection rules. Like delta J can be plus or minus 1. Delta V, can be plus or minus 1. It can actually be plus or minus 1 and plus or minus 2. Those are called overtones. They're harder to find. But spectroscopically, these transition rules are based, or selection rules are based on the transition dipole moment, which we know only to a good approximation. Rigid rotor, harmonic oscillator, electronic transitions. So there's quantum hidden underneath all of this. But I want to dive in a little deeper on how do we connect what we've just learned to this picture, okay? And it starts with what is psi. Okay. The other thing I want you to think about, and you're gonna love this molecule. It's a rite of passage to do the HCl problem. Think back to the classes that you've taken before, like, I don't know, the soda lab or the penny lab you did with Deanna, project whatever aqua snake python monster thing you did with Stefan. I don't remember. I don't know what y'all do with Graham. But this is the problem. You are going to determine the bond length, the rotational constants, the vibrational constants, I think the dissociation energy. There's one more. Polarizability. I think that's it. Of this molecule and this molecule. Just from spectra. So all of those tables in your Gen Chem textbooks that give you the bond lengths, guess where you get them from? Quantum mechanics. Okay. Anyway, this thing's oscillating. It's a dipole. It has an oscillating dipole moment. Okay. And so dipole moment, not to be confused with transition dipole moment, is charge across a distance. And so as this distance expands, that dipole moment changes. There's an oscillation there. Okay. As there's an oscillation, you're going to have some wavelength of light coming in that has both an E field and a B field. There is a superposition of this oscillation with this oscillation of the dipole moment that's going to transfer momentum. Okay, because those energy states are the same, there's a momentum that can be transferred, and that only occurs when you've got that transition dipole moment being overlapped by the oscillating electric field of that light as it overlaps this oscillation of this dipole moment. Okay, go team. Last thing I want to say about this, depending on what this is, if it's the dipole moment derivative, it's IR. If it's the polarizability tensor, it's Raman. If it's the if it's just the electron wave function, well, basically the charge of the electron at a particular distance, it's UV vis. It's all the same. Okay, go team. So let's dive deeper into psi. What is psi?